Thank you very much. Yeah, good afternoon. First of all, let me thank for a very kind invitation to this wonderful workshop on this focus of antiferromagnets. Now, I have decided to focus on the relationship between spin-polarized scanning tunneling microscopy and antiferromagnets because antiferromagnets actually played a key role in the development of spin-polarized STM on one hand, but on the other hand, as we will see, the spin-polarized STM technique also provided detailed insight into atomic scale properties of antiferromagnets. Now, what is spin-polarized scanning tunneling microscopy? This is a technique where we actually make use of a magnetically functionalized probe tip so that at the very end of this tip, a single atom basically carries a well-defined spin with a very well-defined spin orientation. This is crucial. And then we measure basically the spin-dependent part of the tunneling current here flowing between such a magnetic tip and a magnetic, in this case an antiferromagnetic sample. And actually, the spin-dependent part of the tunneling current depends then on the cosine of the angle between the local surface magnetization and the tip magnetization orientation. So basically, we measure a local projection of the local surface magnetization onto the quantization axis, which is given by the spin orientation of a probe tip. And so it is extremely important to have full control in three-dimensional space over the spin direction at the front atom. That is at the heart of this technique. And then the spin contrast is basically determined by the spin polarization of the states of both sample and tip. Now, actually, when I introduced this technique in the early 90s, I first started to look at different operation modes which are useful to combine atomic structure information, electronic structure information, and spin structure information at ultimate spatial and energy resolution. Later on, we also added the time resolution. So actually, as we will see at the very end of the talk, we can even go down to the femtosecond regime these days. Now, the first operation mode, which was introduced 27 years back in time, was one which basically makes use of the constant current mode. This is the conventional mode of STM operation. And the idea was that we can basically transfer the tunneling magnetoresistance effect into an effect of an apparent topographic height change in an STM, simply because in the situation where we have a parallel alignment of magnetization in the tip and locally on your surface, we would have, of course, a low tunneling gap resistance then, whereas in the case of an antiparallel alignment, of course, the resistance would be higher, meaning the spin-polarized part of the tunneling current would be smaller, and this means that in a constant current mode, the tip has to go closer to the surface. And so you get basically an apparent height change, as you can see here, even if the surface is atomically flat and where you only have this kind of domain structure. So in principle, you can, of course, study this for a domain structure of a ferromagnetic material, of a ferromagnetic thin film, as we did later on. But at the beginning, actually, we made use of an antiferromagnetic material. And historically, that was motivated by the fact that we wanted to exclude basically magnetic dipolar interactions between the tip and the surface, because we did not want to have a kind of magnetic contrast which was known from magnetic dipole force microscopy. So the first system actually which we have chosen was the chromium-001 surface, and it was predicted theoretically by Stefan Blügel in a nice paper end of the 80s that this chromium-001 surface should exhibit a so-called topological antiferromagnetic order if you have a surface with monatomic steps. In this case, because of the structure, of course, of chromium being an antiferromagnet, you then expect to have ferromagnetic 001 terraces, but then if you go one step down, of course, you end up with another ferromagnetic terrace with an opposite magnetization. And this test structure is, of course, extremely useful if you have no external magnetic field, for instance, which would be useful, of course, to reverse the magnetization. This is a natural test sample which you can make use of to test the basic principles of this technique. And this was applied basically end of the 80s already and published in 1990, where we basically have seen when in addition to these monatomic step heights, we could see a clear periodic alternation of the measured step heights. So this periodic alternation was exactly due to the spin-polarized tunneling effect, and the differences then between the measured heights and the structural heights, which you expect, of course, could be directly related to the spin polarization of tip and sample. Of course, you cannot only make use of the constant current mode, where you see basically the apparent height changes, but very soon after, we also look directly at the spin-resolved tunneling conductance. So here you see basically one of the first traces of the spin-polarized tunneling conductance when scanning over this topological antiferromagnetic ordered structure. And you see at that time with rather low signal to noise, but nevertheless you see the periodic alternation of the signal from one terrace to the next. And you have a quite high contrast simply because you have a highly spin-polarized dz square-like surface state for this chromium 001 surface, and this helps you actually in getting quite nice spectroscopic contrast, because if you sit then basically at a bias voltage corresponding to this highly spin-polarized electronic state, you can of course get very nice magnetic contrast. And this is shown here, where we make use now of the combination of spin-resolved tunneling conductance measurements and of course the spatial resolved scanning. And here you see a beautiful image then taken by my student Michael Kleiber and reported 10 years later after the constant current mode was established, where you clearly see here the nice alternation here of the spin-resolved tunneling conductance signals following, of course, this step and terrace structure of the chromium 001 surface, which you can see above. And at that time already we have improved on the signal to noise level here considerably, as you can see from a single line section here across these terraces. Now, we were able then also to look at larger scales. Not only could we look to the perfect antiferromagnetic ordering here for the different terraces, but we could also look at the influence of step dislocations and screw dislocations. So clearly, around the screw dislocation, the magnetization has to make a turn by 180 degrees, which could be nicely mapped here, and also more sophisticated defect structures and their influence on the surface magnetization could be mapped. I would like to point out that these early experiments were actually the first to use antiferromagnetic materials in any type of magnetic tunnel junctions. And moreover, since all the early work in the first 10 years were basically all done at room temperature, actually that was also the very first work which showed that magnetic tunnel junctions can be operated at room temperature. The work for planar tunnel junctions were much later in 94, 95, but this work basically was the first to use antiferromagnetic materials in any type of tunnel junctions and even at room temperature. You might ask, this temperature is pretty close to the baric nail temperature. However, at the surface, the nail temperature is enhanced, and that was shown independently by other groups that we have a surface enhanced nail temperature. This is why we can get very strong contrast still at room temperature, and of course later on we even went up well above the baric nail temperature and could still resolve this very nice surface structure, confirming that we have a significant enhancement of the nail temperature at the chromium 001 surface. Now, interestingly enough, this basic principle did not only work for, say, nanoscale structures like these terraces, but you can really scale this down to the atomic level, which you can show, of course, if you have an in-plane antiferromagnetic structure, like, for instance, a single layer either of manganese or chromium, in this case on a tungsten 110 surface. And in this case, you can really show that this basic principle of spin-polarized conductance variations work down to the atomic level. And you can really probe the spatially resolved local spin density in a vector resolved fashion. So the kind of images you have seen this morning in the nice talk of Professor Gross, this kind of picture actually can be taken nowadays with spin-polarized STM with subatomic resolution. Now the basic principle then on this atomic scale is very nicely illustrated in this animation, which was made actually by Stefan Heinz. So here basically we have a schematic drawing of such an in-plane antiferromagnetic structure as realized, for instance, by a single atomic layer of manganese on a tungsten 110 substrate. And then we approach this tip with a very well-defined spin orientation, measure basically the spin-polarized tunneling current flow here across the tunnel junction, and one can see then that this tunneling magnetoresistive effect can be measured also on the atomic scale. You can see the variation in spin-polarized tunneling current flow here on the atomic level. And again, the constant current mode has been used then again to transfer the information about the spin quantization in space into an apparent topographic height change. Meaning that if you scan now this surface with your tip, the tip has to go up and down now with the periodicity of the magnetic unit cell, not of the chemical unit cell, as you would, of course, do with a non-spin polarized tip. And of course, you can see then side by side what you would get with a non-magnetic conventional STM tip, for instance, a tungsten tip, where you resolve the atomic lattice, and of course you see the chemical unit cell here with such a non-magnetic tip, whereas with a magnetic tip you can really see here the enlarged magnetic unit cell, here in this case in very nice agreement with theoretical ab initio calculations done at that time of Stefan Heinz together with Stefan Blügel. Actually, it was shown at that time based on ab initio calculations, taking into account spin-orbit coupling already at that time, that one would expect actually this C2x2 antiferromagnetic structure with an in-plane magnetic anisotropy for this single atomic layer of manganese on tungsten 110, and this is energetically preferred compared to a ferromagnetic state or to this P2x1 antiferromagnetic structure. However, this was not the end of the story for this particular system of a single monolayer of manganese on tungsten 110. In the following years, we improved the signal-to-noise ratio drastically, not just by improving on the electronics, but particularly by improving the tips, the spin polarization of the tips, so that we could enhance basically the spin contrast. And then it was possible with much better signal-to-noise to scan larger areas of that particular sample. And now you see basically comparison of the previous image you have seen, where we see locally this antiferromagnetic ordering. But if you look at large scales, you see that there is not only a short wavelength period corresponding to the antiferromagnetically ordered state, but there is an additional modulation with a 6 nanometer periodicity here, meaning that there is not a strict collinear antiferromagnetic ordering here observed, but in addition, of course, an additional structure. And we could prove that this additional modulation is due to a spin spiral. A spin spiral in an antiferromagnetic system here with a period of about 6 nanometer. You can rigorously prove that by doing experiments with different spin alignment at the front atom of your probe tip. And then you can basically distinguish between such a spin spiral state and, for instance, a spin density wave state. So this is crucial, of course. And the interesting point was that by looking at these spin spirals on this manganese on tungsten 110, we could always find spin spirals with the same sense of rotation. So the mirror image of such a spiral was never observed. So for all samples and for all areas which we were looking at, we always found the same sense of rotation for these antiferromagnetic spin spirals in this system. And that was similar to the earlier work we did, 5 years earlier actually, where we discovered for the first time chiral domain walls in the system of 2 monolayers iron on tungsten 110. And the interpretation of this, as we know these days, is of course the interfacial Dzerzhinsky-Maria interaction, which is decisive basically to explain this chiral structure of these spin spirals as well as of the domain walls in these thin film systems. And particularly if this Dzerzhinsky-Maria interaction becomes of similar order of magnitude as the symmetric exchange here, then of course we have especially very short wavelength spirals. And we have seen that this is not unique for this manganese on tungsten 110 system, but can be quite generally observed. So in the following years, we basically made lots of studies where we have been using tungsten substrates in different orientations, but also iridium, more recently rhenium and other kind of substrates. We also looked to various transition metal films, not only manganese, chromium, iron, and so on, but also bilayer systems like palladium iron, rhodium iron, lead iron, and so on. So I can add another 10 examples at least here. So that's a quite unique feature that due to this interfacial Dzerzhinsky-Maria interaction, the system tends to exhibit such non-collinear spin states. However, it is not true to reverse this and say, oh, we should always expect some non-collinear states. And I give you now a true example of a really collinear antiferromagnetic structure, and this is seen in the system of a single monolayer of iron on a tungsten 001 substrate. This is quite amazing because you would expect iron as a prototype ferromagnet would be in a ferromagnetic state, as indeed is observed for a single iron layer on tungsten 110. However, for iron on tungsten 001, it was predicted very early on by Art Freeman in the US that there should be an antiferromagnetic ground state, but there was no technique available to prove that. So we thought that this is really a very nice test case, so we prepared a sample with about 1.3 monolayer coverage of iron on this tungsten 001, so that you can see some second layer iron islands, which were known to be ferromagnetic. And we did this kind of preparation so that we could basically calibrate our spin-polarized tips. So you see that with an in-plane sensitive tip here, we see basically the 4 different colors because of the 4 different spin-resolved conductance levels, which result from the 4 different orientations of the magnetization in this 4-fold symmetric system. So truly these are just ferromagnetic islands with in-plane magnetization in 4 different directions being orthogonal to each other. Now if we now go to the monolayers in between these double layer iron islands, we see that with an in-plane sensitive tip we just get a 1-by-1 structure, as you would see with a non-magnetic tip. And here you see how important it is to control the spin orientation, because only after we magnetize the tip now in the vertical direction along the tip axis, meaning perpendicular to the surface plane, we could resolve this very, very nice C2-by-2 structure, which actually results from an antiferromagnetically ordered state as predicted by Art Freeman. But the additional new ingredient from the experiment was that we have out-of-plane spins here, in contrast to the case I discussed before for the single manganese monolayer on tungsten 110. Now, of course, to rigorously prove that this is a spin contrast image, you have to do this experiment, which is the standard experiment always to do, that you reverse the magnetization in your tip, and then you should be sensitive to the 2 different spin sublattices of the antiferromagnet, either to the red spin sublattice here, where we have now the parallel spins, or here the green spin sublattice, where here, in this case, we have the parallel spins here with the tip. And if we do now the spin-resolved contrast imaging with these 2 kind of magnetized tips, we can get 2 data sets, and we are using typically then single atomic adsorbates to make the registry between these 2 images. And of course, if you look carefully, you already see the phase shift. However, of course, you should do it quantitatively, so we can just calculate the difference of these 2 data sets. And then in the difference image, you can nicely see the Néel-ordered state, in this case on a square lattice, whereas the topography results just from the sum image. If that would be a surface reconstruction, it would just be the other way around. The sum image would, of course, enhance the superstructure. The difference image would show nothing. So that was rigorous proof of the spin contrast here for a Néel-ordered state on the square lattice. To my knowledge, it was the first real space observation of this kind, and we could do so not only locally, but because of a significant improvement in the signal to noise, we were able really to observe large-scale images with atomic resolution spin contrast, which you see here still. But you see that on larger scales, of course, you have atomic defects, you have vacancies, you have impurities, you have adsorbates, you have single iron atoms on top and clusters, as well as these second layer islands. But nevertheless, if we scan, and we did this really over several tenths of micrometers by really putting together a large number of atomic resolution images, we could see the beautiful coherence in the spin lattice here really over mesoscopic distances. So there was no domain boundary here, which we were actually looking for at that time. We saw basically a perfectly coherent spin lattice here in this case. However, we then prepared samples where we could actually see interface domain boundaries in this antiferromagnetic layer of iron on tungsten 01, and we report about this 10 years back in time, where you can see here with atomic resolution now the structure of such an atomic resolved domain wall here in this iron monolayer on tungsten 01. Basically, this domain wall width is only about 6 to 8 lattice sites, and we basically did then Monte Carlo simulations with the DFT parameters as an input and compared then the simulated spin-polarized STM images based on these Monte Carlo simulations with the experimental data, and really found a very, very nice agreement. So at that time, this publication was not so well recognized, but in the meantime, a lot of theory groups actually were working on domain walls in antiferromagnets, and so this work is much more recognized these days. However, I would like to stress that the world of antiferromagnets is, of course, not limited to simple transition metals. The next case I would like to discuss is particularly the compound of iron telluride. Why is that? Because it's the parent antiferromagnetic compound of very interesting superconducting materials these days. So if you dope the system with selenium, you can turn this antiferromagnet to a very nice superconductor. Also, there's, of course, another compound, iron selenium, which is also known, of course, to be a superconductor. However, iron tellurium, in the bulk at least, is just an antiferromagnet with a bulk nail temperature around 70 K, and there's no superconducting phase known for the bulk material. Now, this type of compound and related compounds has recently attracted our attention, and particularly we prepare these kind of iron chalcogenide systems now on topological insulators of the class bismuth 2 tellurium 3. And we actually use a very nice and straightforward way to prepare atomically well-defined films by just depositing now iron by e-beam evaporation under very well-defined UHV conditions onto these substrates. And now what happens is that the tellurium actually prefers to bind to the iron rather than to the bismuth. So then you can basically get very nice either embedded on top tri-layers of this iron tellurium on top of the bismuth 2 tellurium 3. You can do so in a similar fashion also for the selenium-based compound, and also for the ternary compound, by the way. And this is a very nice way to get very well-defined interfaces now of these kind of iron chalcogenide films and these bismuth-based topological insulators. Here you see, first of all, an overview STM topograph where we still have some terraces of the bare bismuth 2 tellurium 3 111 oriented surface, as well as some embedded as well as top unit cell layers of this iron tellurium. And you see that by zooming into these terraces of the substrate, you see, of course, very nicely the hexagonal symmetry of the atomic lattice, because it's a lattice with 111 orientation. You see the 6-fold symmetric spots in the Fourier transform, and you beautifully can observe bright spots. These are the dopant sites in this bismuth 2 tellurium 3 lattice. Now, if we grow now this iron on top and zoom onto these iron tellurium areas, then you see immediately the change in the symmetry of the lattice. Now we have a square lattice, as it should be for iron tellurium. You see beautifully the fourfold symmetric spots. And in addition, we also see some modulation of the density of states which result from interfacial doping via the substrate. So this is, of course, at the heart of what I would like to discuss later on, namely that we observe interfacial superconductivity, which has to do with this interfacial doping from the substrate. You can do so also for the ternary system, iron, tellurium, selenium. This is a very well-known bulk superconductor with a TC of around 13 K, and you can prepare highest quality ultra-thin films of this material in this way on topological insulators. Now here you can see the beautiful atomic resolution images, of course, of these iron tellurium films as a function of thickness. And of course, you can then add the spin contrast, and this is, of course, at the heart of what we want to see. So by using now a spin-sensitive tip, we see immediately the reduction of symmetry in the pattern we observe. Now we have a row-wise structure here, and immediately we see only the twofold symmetric spots in the Fourier transform. And now we do the same thing as discussed before for the antiferromagnetic monolayer of iron on tungsten 001. We change the magnetization direction of our probe tip, and you see then again a phase shift, which again becomes clear if we calculate the difference image of these two data sets, and then we basically get a pure spin contrast image here, and you see beautifully this row-wise structure. In this case, actually, we have two rows of iron sites with the same spin orientation, followed by two rows of iron sites with the opposite spin orientation. So in the literature, this is referred to as a bicollinear antiferromagnetic state. And the beauty is that we can resolve that even for a single unit cell layer. Of course, this has been observed by other groups and also by us at the surface of bulk iron tellurium. But the new finding is that you observe this bicollinear antiferromagnetic state even for unit cell layers. And even more surprising is that the Néel temperature of the single unit cell layer is exactly the same as for the bulk, meaning that the relevant magnetic interactions are within the plane of this layer, and that basically the interlayer couplings in this system do not play a role at all. So you can study the thickness dependence of the spin contrast, the temperature dependence. It's basically the same up to 70 K. Here I show data for 1 K up to 10 K, but in the meantime we went up to the bulk Néel temperature. Now, even more surprising is that you can then look at the interfaces between these antiferromagnetically ordered thin film and the topological insulator substrate. And we see clear evidences now of a gap opening. So you see a gap structure here right above the iron tellurium, which disappears if we scan now across this interface and go over the bismuth 2 tellurium 3. Since we have directly access to the atomic resolution lattices, we can, of course, immediately assign the different areas. And you see that this is obviously no tip-related effect because we are scanning both areas exactly with the same microscopic tip. Now, we did very careful studies now of the temperature, field dependencies, and so on. And the interesting point is that this gap feature, which we observe for the iron tellurium, basically starts to disappear already here if we go to 2 and even 3 unit cell thick layers. On the other hand, if we look at the temperature dependence here and study this here quantitatively, we can observe basically that this behavior follows nicely a BCS type behavior. We can do a very nice fit yielding a transition temperature around 6.5 K. We can do so for the related ternary compound, which is shown here. Here, of course, we have to admit that the gap is much more pronounced. We have a U-shaped gap with much more pronounced coherence peaks here. But the temperature dependence is very similar here, and basically the fit yields now a transition temperature of 11 K for the ternary system, which is close to the bulk TC value of around 13K. So this is not so surprising because the bulk system is superconducting, but here this is really a surprising result that we find clear evidences for interfacial superconductivity. Of course, you always have to consider other kind of explanations. You might consider a Condor lattice state for the iron tellurium, but you see if you compare with here numerical renormalization group theory results, the temperature dependence which you would expect for a gap induced by a Condor lattice state cannot describe the temperature dependence of a measured gap here. This is the BCS fit, and it only can basically explain this behavior. We do these kind of investigations now for other kind of antiferromagnets which are parent compounds to high TC materials. But as you all know, in many cases you start with insulating phases. Insulating phases which are not even accessible with tunneling microscopy techniques. And so I would like, of course, to stress that 10 years ago we introduced a second technique which allows to combine atomic resolution and spin sensitivity, which is magnetic exchange force microscopy. This technique should not be mixed up with magnetic force microscopy, which measures dipolar magnetic interactions, but in this case we measure short-range exchange and correlation forces between an atomically sharp probe tip in very close proximity to a surface. So basically we have to get very close, like in tunneling microscopy, to have an overlap of wave functions of both tip and sample, but instead of measuring a current, we measure forces. And here we used as a first test case the very well-known nickel oxide surface in 001 orientation, and you can beautifully see in the real space data, but also in the Fourier transform of the raw data here, these additional spots which relate to the antiferromagnetic ordering here. And you can compare, like in the case of the manganese monolayer on tungsten 110, what you expect if you have only chemical contrast with conventional non-contact atomic force microscopy, which in this case is sensitive to the oxygen sites primarily. So the bright spots are the oxygen sites. Why? Because we were using metallic coated tips, and metallic coated tips are typically sensitive here to the oxygen sites. Now if we go to a spin-sensitive tip, you see now in the real space image, of course, that we have now a superstructure. And of course, if we look at individual line scans, you see now that we get contrast at the minima, and this is exactly how it should be, because these are the metallic sites, the nickel sites, where you expect to see the spin contrast. But I would like to highlight that these apparent height changes are extremely small. So this scale is given in picometers. It's a 1.5 picometer height difference. So it's really difficult to detect this, but nevertheless, currently we apply this also routinely to many different classes of materials. We have recently also measured skyrmions for the first time, which we can now also look at in oxidic type of materials by making use of this technique. So it's a perfect, of course, complementary technique to spin-polarized STM. So in the very last part of the talk, maybe I have 2 minutes left, I would like to discuss now what we can do on the single atom level, going towards atomically engineered antiferromagnets, where the idea is to use antiferromagnetic spin chains to transmit information, to basically create logic gates, and so on. Now here the challenge is even higher, because we do not only need atomic resolution, but we need single atom sensitivity. And moreover, you cannot use any ferromagnetically coated tip anymore, because even the stray field of, say, 1 or 2 monolayers of a ferromagnetic material on top of such a tip is too large. It would immediately perturb the magnetic state of individual atoms or molecules. So we turned now the situation around. Ooh, this is not displayed nicely, but you can see that basically partially, that we now turn the role of sample and tip around, and this is of course also at the heart now of antiferromagnetic spintronics, that we can also make use, of course, of pointed tips, atomically sharp, from an antiferromagnetic material. Now the advantage is that you have no stray field at all at distances here of about 10 angstroms. And on the other hand, if the tip is atomically sharp, which you need anyhow for atomic resolution STM imaging, you always have, of course, one single atom, with a given spin orientation. And it's the spin orientation of this front atom which determines the magnetic contrast. The other atoms, which have an opposite spin orientation, do not contribute considerably to the towing current because it's exponentially dependent on distance. So actually these atoms contribute only a fraction to the towing current. So it's just this front atom spin which is decisive. And with this kind of new tip, atomically sharp of an antiferromagnetic material, we could then do fantastic experiments where we could introduce single atom magnetometry. There are a lot of techniques these days around claiming nanoscale magnetometry, but actually we demonstrated single atom magnetometry already 8 years back in time by positioning such single atom antiferromagnetic probe tips above individual magnetic atoms. And by looking at the response now in the spin-polarized tunneling conductance to an external field, we could either observe the characteristics of a paramagnetic impurity or, of course, of basically ferromagnetic nanostructures. So here quickly is the result which you would get for such a ferromagnetic nanostructure. It's basically a stripe of cobalt here. You see even two different domains in the spin contrast image. And what we are looking at is now the coupling of individual atoms to this cobalt ferromagnetic structure via a non-magnetic substrate, in this case platinum. So you see beautifully this magnetization hysteresis here for the ferromagnetic cobalt nanostructure. This is just recorded by measuring the spin-resolved tunneling conductance as a function of field. And now you can do so above the individual atoms. And interestingly now, because of the coupling, by indirect magnetic exchange, we see an opening here of the hysteresis here. So it's not a paramagnetic impurity anymore. We see a hysteresis on a single atom. And moreover, if you look now to the different branches of this hysteresis curve, you can recognize that this atom B is ferromagnetically coupled, whereas atom A and C are antiferromagnetically coupled. Now, if you do this analysis now for hundreds of adatoms here, which you can find at different distances, you can then extract then the indirect magnetic exchange coupling as a function of distance. And surely this type of interaction cannot be explained by a dipolar interaction, but it's a well-known oscillatory type of magnetic exchange coupling which we observe here. And the beauty is that you can then identify exactly the distances which are needed for an antiferromagnetic coupling. And we could do so not only for the coupling between atoms and nanostructures, but also between atoms in a pair. For instance, this is a cobalt pair on platinum, where we see for this distance regime given here and here that we have a ferromagnetic coupling, whereas for this distance regime we observe an antiferromagnetic coupling extracted from the single atom magnetization curves. We can immediately check, of course, whether this interpretation is correct, because we can go from a topographic imaging now to a spin contrast imaging, and you see that now for this dimer existing both of cobalt atoms, we see an amazing spin contrast here on the individual atomic level, which is just due to the different spin alignment of the two cobalt atoms. And this we could show, of course, as a function of the length of these chains, 3-atom chains, 4-atom chains, 5-atom chains. If you have an odd number of atoms, of course, you have a residual spin then on these type of chains which can couple to an external field. So by changing an external field orientation, you can go from an up-down-up to a down-up-down configuration as it should be. You can all resolve that directly in real space. You can construct larger chains and look at the response in external field. So by sweeping the external field, you can basically detect what kind of Zeeman energy is needed to overcome the indirect magnetic exchange coupling energy, and this is a way how you can quantify the coupling. Once you have understood this, you can go to more sophisticated structures, quantum correls made up of antiferromagnetic arrangements of iron atoms on copper. Again, you can go to the ferromagnetic version, but in higher fields. You can build up unit cells of Kagome lattices or also extended Kagome lattices based on antiferromagnetically coupled atoms. And again, amazing is the fact that the single atom magnetization curves for the same atoms at exactly the same adsorption site looks so much different simply because of the neighborhood, the interactions with the neighboring spins. And so in these single atom magnetization curves, we have a huge amount of information about these couplings. And once this is all understood, and this is the final point I would like to make, you can really go into the direction of devices, and this is in the end, of course, the final goal. So this was the first demonstration of a single atom all-spin logic gate. This is work by Alex Khachaturian, which we reported already 5 years ago, where we made use of ferromagnetic islands as input gates, and then we basically then transferred the information along antiferromagnetically coupled spin chains to a central region where we could do the computation and then use this atom as an output state atom, which we were looking at in response to a magnetization change in the input gates. And here you see the construction atom by atom of an antiferromagnetic spin chain, making use of the knowledge which kind of distance you need to get the antiferromagnetic coupling. And you see the huge contrast change. They are all individual iron atoms sitting on an equivalent adsorption sites, but the contrast is huge here. It's a perfect antiferromagnetic spin chain, and you can even observe once you switch the magnetization now of the input gate how the spin information is propagating along these antiferromagnetic single atom chains, and so this influences the output state of that atom. And this way we were able basically to demonstrate all kind of logic gates, OR gates, NOR gates, AND gates by just looking at the output state atom as a function of the various types of input states. The beauty, and this is the summary, is that these all-spin atomic scale logic gates basically fulfill all the promises of spintronics, but now at the atomic level. They are ultimately fast because the time scale it takes for a single iron spin to flip on such a copper surface is only 200 femtoseconds, which we measured directly with time-resolved STM. And moreover, for these spin operations, we have almost negligible energy dissipation. And moreover, contact properties are totally irrelevant because we only operate on the spin degree of freedom. There's no charge transport here, so we don't have to worry about contact resistances. So here in the end, you see the comparison of the scale of this tiny spin logic device in comparison to the single gate of a planar transistor in 32 nanometer process technology. And this brings me to the get home message. There's certainly plenty of room here at the bottom for antiferromagnetic spintronics. So in the end, I would like to thank my co-workers involved in this work, and I would like to thank you for your attention.
We have minus 15 minutes, but maybe we have one question.
In your iron tellurium investigations, did you see any indication of increments in that structure, magnetic or strongly non-collinear? Because in the bulk under stoichiometry, this is agreed.
No, we saw also on large scales, which we did, of course, a perfect bicollinear antiferromagnetic. So you see in the literature a lot of results, for instance, where people claim to have spin density wave phases, also outer planes were charge density wave states for these iron tellurium films. None of these things are compatible with our observations. It's just bicollinear antiferromagnetic orbital state as we have in the bulk, and we do not see any indication here for spin density wave or charge density wave state.
Yeah, we have shown very impressive work with ferromagnetics, also with antiferromagnetics. As a principle, you may also use in non-magnetic.
Exactly. Thank you for the comment. The time was too short. In fact, you can make use of spin-orbit coupling. This is the hot topic these days. Yeah. So on one hand, you can make use of the so-called tunneling anisotropic magnetic resistance effect, which means that with a non-magnetic tip, you can observe, of course, the difference of an in-plane magnetization and the out-of-plane magnetization because there's a spin-orbit coupling effect to the bias structure. And if we tune the bias to the right machine, where we see the effects of spin-orbit coupling onto the band structure of our magnetic material, then we can beautifully, and we have demonstrated that already 14 years back in time, it was PL in 2002 already, that we can, for instance, image domain walls or other kind of systems with tungsten tips. However, you cannot say something about the direction of magnetization, whether it is up or down, or left or right. So, for instance, if you want to analyze current structures, you need the spin resolution, the vector spin resolution. So, still, of course, in the end, I always prefer Spin-Polarized STM. And there's even a new magneto-resistive effect which we have reported on last year, which is called non-collinear magnetoresistance effect. And this is again something else. This magnetoresistance effect actually depends on basically the degree of non-collinearity, which you can describe basically by the magnitude of the gradient in the magnetization profile. So the larger the gradient is in the magnetization profile, the greater is this additional contribution to the resistance. And this is a way, for instance, to image objects like skarmions, which are highly non-collinear objects with non-magnetic tips. So everybody can look at skarmions even down to the single-digit nanometer length scale by just a conventional STM. However, you cannot prove the chiral nature of the objects. For this, you really have to do spinning so much.
Okay. Just think,